we talked about on Friday was we started on atomic structure. And we talked about the development of the atomic model. We talked about the definition of what a model, what the atom was. It was a Greek word that meant indivisible or uncut. And it meant that we had something that we could divide down to its smallest possible amount, and we couldn't divide it down any further than that. If we tried to divide it further than that, it became something altogether different. Like helium has the atomic number of 2. It's got 2 protons in the nucleus. If we divide that down, one helium atom in half, it became 2 hydrogen atoms. So 2 totally different things. So the smallest amount, or the smallest portion of something we could divide out was what the Greeks called an atom. They didn't really understand what an atom was, and so they had the 4 essences. So we went from Greek model to the Dalton atom, and the Dalton atom, his model introduced us to combining of different types of atoms to create something different. Like whenever we have water, we have 2 parts hydrogen, 1 part oxygen, so we have H2O. We divide that down, and again, we've got 2 parts hydrogen, 1 part oxygen. But the combined form of that is kind of what Dalton gave us. Then we had the Thomson atom. Thomson atom was a little bit weird with the plum pudding thing, but it introduced us to 2 different components to the atom where we had a well-defined nucleus, and then we had electrons outside of the nucleus. So that was his contribution. The Thomson atom kind of built off I'm sorry, that was Thomson atom. The Bohr atom was totally different. It built a little bit off of the Thomson atom in that we have a well-defined nucleus, but the electrons were not stuck to the nucleus. They were outside of the nucleus in prearranged shells and orbits around the nucleus itself. So what we looked at in the Bohr atom was that it resembled a solar system where the sun represented the nucleus and the planets were representative of the electrons in their shells. Where that model fails, or not the model, but the analogy to the solar system we're going to talk about later today. In the solar system, we only have 1 planet per shell. And we've got moons, but 1 planet per shell, 1 planet per orbit. So the bulk of the mass is inside the nucleus. Most of the area of an atom is empty, and the electrons exist in an orbit. They live outside of the nucleus in orbit. So when we talked about the fundamental particles, we had protons, we've got neutrons, we've got electrons. The protons and neutrons are what we call nucleons, and they're inside the nucleus of the atom. Electron is outside the nucleus. So then we talked about atomic nomenclature, basically, or what the subatomic particles that we're interested in are. There's hundreds of them, but we're only going to focus on 3 because they're really the only 3 that matter for our purposes for imaging. And that is the nucleons, the protons, the neutrons, and the electrons. So we talked about the atomic mass unit. The atomic mass unit is the actual mass of the subatomic particle. So the atomic mass unit of a proton was 1.00 and so on. The atomic mass unit of an neutron was also 1.00 something, but it was slightly larger than the proton, which we'll get to it here in a bit. And then the electron was so small that the atomic mass unit was 0.000 something, right? So the proton and the neutron are massive in comparison to the electron. And we talked about the atomic, that was the atomic mass unit. The atomic mass number is just a rounded off version of those. So if you round even 1.09 even to the nearest whole number, what's your number? 1.09 would be 1, right? So the atomic mass number is the rounded off atomic mass unit. So proton, neutron has an atomic mass number of 1. The electron has an atomic mass number of 0. It's so small it doesn't even have an atomic mass number. But there are 3 charges. In the proton, we've got a positive charge. In the neutron, we've got a neutral charge. But what I was talking about on Friday was that I want you to be thinking of the neutron as not having a neutral charge because it lacks charge, but because it has both positive and negative charges inside of it. And we'll talk about that here in a bit. Or really, we'll probably talk about it on Friday. So we've got positive charge is a proton, lives inside the nucleus. Neutral charge has positive and negative charge. That's the neutron, lives inside the nucleus. Electron is outside, and even though the size difference between the proton and electron are massive, the charges are equal, okay? So your atoms want to be neutral, which means that if I have 1 positive charge, then how many negative charges am I gonna have? 1, right. So if I have 1 positive charge, 1 neutral charge, how many negative charges am I gonna have? 1. If I have 1 positive charge, 2 neutral charges, how many negative charges am I gonna have? 1, right. So protons and electrons should equal, right? So if I have 2 protons, should have 2 electrons. Neutrons just don't even play into it. They'll play into something here in a bit, so we'll talk about that. So I talked about the periodic table was developed by Dmitri Mendeleev. There's 118 elements organized just for now, and they're organized according to behavior. If more become discovered, then we'll have more elements. If more are created, then we'll have more elements as well. So in an atom, what we talked about was the atomic number, and we'll talk more about that today. The atomic number defines what the atom is, okay? So if you're looking at your periodic table, what you'll see is that they're arranged, but each one has a sign, right? It's got a chemical symbol, like hydrogen is H, helium is He, but they've got an atomic number, and the atomic number of hydrogen is 1. It has 1 because it has 1 proton. Helium is 2 because it has 2 protons, and so on and so forth, okay? So the atomic number is determined by the number of protons. Number of protons, just number of positive charges. Again, we'll talk more about that here in a bit. So we can have any number of neutrons. We should have the same number of protons and electrons. If we have a different number of protons and electrons, if we have a discrepancy between those two, if we have 2 protons, 3 electrons, what's our charge? It's negative. It's -1. So what is a charged particle called? It's not. Right. Okay. So any questions on those?
I just have one question.
Shoot.
So like Greek atom is 4 essences. Is that the fire, air, water, this earth,
Yeah.
and then it says hot, cold, wet, dry? That's just the.
Yeah, the 4 states of being.
Okay.
Yeah. They, tried to describe it the best they could. Again, I'm not real sure how you have dry water and hot ice. Whatever. It worked for them though. Okay. Any other questions? All right. So again, we're talking about the atomic structure of nucleons. Nucleons being what's inside the nucleus. That's your protons and your neutrons inside of the nucleus. The electrons being on the outside of the nucleus. So again, it looks kind of like the solar system in that we've got a well-defined center, right? So the nucleus, that's where your protons, your neutrons exist, and then you've got electrons around the outside of it. And every time I draw this, you got to understand that it's nowhere near to scale. If you listen to the recording from Friday, you know that the distance between the nucleus and the first ring is way far apart, right? So if this was the size of a basketball, the first ring may be all the way down at Posados if you're from Tyler. It's a massive distance. So mainly empty space. Now what we're gonna learn is that the more protons that we have, and really not so much the neutrons, they add some weight, but really the protons, what we're gonna focus on for this particular thing, the more electrons we're gonna have. And so we're gonna have to add shells. You know, if we had another planet, and it were to fall into the orbit of one of the existing planets, what's gonna happen eventually?
Gravitational pull.
Gravitational pull is gonna pull them together, we're gonna have one big planet and a lot of dead people, right? So, what we're gonna have is if we add more protons, we're gonna have to add more electrons, and what that's gonna result in, as we'll take a look at here in a minute, is more electron shells. But what I want you to be thinking of is that as the size of the nucleus gets bigger, and especially the more protons we add, that, yeah, we get more shells and we're probably gonna expand out some, but it's not gonna be as much as what you might think in that, let's say we've added 2 more protons, we're gonna add 2 more shells out this way. Instead, what you need to be thinking of is that the electron cloud gets a lot more compact, okay, which is gonna play into our favor. So instead of the overall atom getting larger and larger, you know, with the shells, it does get larger, but it gets much more compact as well. So again, whenever we're talking about 2 different elements and a quantity that looks identical, you've got lead and you've got aluminum. Why would the lead weigh more than the aluminum? Well, that's why. You know, what you've got in the lead is a much larger nucleus with a whole lot more protons and probably a whole lot more neutrons as well. But the electron cloud, the size of the electron cloud didn't grow in size, it just got busier, okay? So it got more dense, it got more packed, so that the overall area of the atom is not all that much larger. What's larger though is the nucleus, and the nucleus is where the weight lives. The mass lives in the nucleus, right? So, the electrons live in shells, and shells are numbered by letter, really, and they're alphabetical, but they start with K. So we got K, L, M, N, and so forth. So, the number of electrons that we can have in each shell is going to be determined by a couple of different things. Where the shell is, right? So we got the K shell being closest to the nucleus of the atom. What we've got is a maximum capacity in the K shell of 2. Now we can calculate the maximum number of electrons that any shell can have with a formula is 2n squared, okay? So that's the number in any shell can be calculated by 2n squared. And you need to understand this is a maximum number that any shell can hold. It doesn't necessarily mean that that shell is going to have that many at any given time. The inner shell most likely is going to max out before it moves out, but eventually the electrons are going to spread out to where even though this is the maximum number in any shell, does not necessarily mean that shell is going to have that many. Does that make sense? Okay, so we've got the inner shell. The inner shell being the K shell. The N represents the number shell. That's K is number 1. L is number 2. M is number 3. Right, so on and so forth. So first shell is the K shell. So how many can we have in the K shell? We've got 2n squared. That will be 2 times 1 squared. 1 times 1 is 1. 2 times 1 is 2. So the maximum number we can have in the K shell is 2. 2, no more. Not ever going to have any more than 2. Only going to have 2. All right? Now, 2n squared, 2n squared. What's the L shell? 2, right? So 2 times 2 squared. What's our order of operation? What's the first thing we got to do here? Yeah, clear the exponent. So we've got 2 times 2. So we've got 2 times 2 times 2. 2 times 2 is 4 times 2 is 8. So we got 8 in the L shell. The M shell is 3. So now we've got 2 times 3, which is 6. Oh, no.
Three times
3. Yeah, I was going 2 times 3. 3 times, yeah. So we got 9, which is 18. Okay? So that's the maximum number that you can have in each shell. So if we went out to the 4th, that'd be 4 times 4, which is 16. 16 times 2 would be 32. So they increase in possible arrangement the further out they go. But again, it does not necessarily mean that you're going to have 32 in the end shell before you start adding on to the O shell. Okay? You're not necessarily going to have 18 in the M shell before you move to the N shell. This is the maximum number that you can have theoretically in any shell is 2n squared. Okay? So you see the difference between those two things, right? You can have that many, doesn't mean you're going to have that many. For example, the outer shell, if you read, if you read the chapter, read this section in the chapter, what does it say the outer shell can never have more than? 8. It can never have more than 8, right? So if you have an atomic number of, let me take his thing a little bit further. It can never have more than 8, and in fact, it wants to have 8. Okay? So it's really two things. It wants to have 8. Its most stable state is for 8 to be in the outer shell. So it wants to have 8, and it can never have more than 8. So if you have something that has an atomic number of 12, how could you make that happen?
You could put, split it up, put maybe 4 in each shell, or no.
You could maybe go 2
Yeah,
to
2 to
8, right? Okay, I'm not saying that that's exactly how that would play out, but that's, in an ideal situation, that's the way it would look. So you would not necessarily fill up the L shell before you started filling up. The M
That
shell.
last one, the 8, is always considered the valence shell, right?
Right.
Okay.
Yeah, valence electrons are important to understand in electricity. They're loosely bound electrons so that they're easy to move, right? Inner shell electrons very hard to move, outer shell electrons easy to move. That's the basis for electricity. You add electrons and they just push them, on and on. So we'll talk about that later in the semester. Okay, so y'all good with this so far? Okay, then we've got 2 forces that hold these things into place, right? And again, we're going to go back to the solar system model to understand these two forces. Again, this is where it fails. We're going to have multiple planets in each orbit around the nucleus of the atom, as opposed to in the actual solar system, we only have 1 planet, if you don't consider the moons, which are really in orbit around the planets. All right, so solar system, 1 planet per orbit. In our model here, we're going to have multiple planets per orbit. All right, so the things that are holding the planets into space, into their orbit, are 2 different things. You've got centrifugal force and you got centripetal force, and they're both working as they're opposite forces, and they're at the same time working together. So if you were to take a bucket, every kid I think has done this. You take a bucket and you fill it up with water. You grab the handle and you spin it around and around and around real fast. Do you get wet?
No.
Not until you slow down. Once you slow down, then it falls down on you, right? Water falls down on you. So what you've got going on there is an illustration of what holds the planets in orbit. You got centripetal force and you got centrifugal force. And you got to have them both. So in the orbit, let's say we're going to change this again to, we got the sun. Get rid of all this other stuff. And then what's the first planet?
Mercury.
Mercury, right. So we've got Mercury. Mercury is very close to the sun. And it travels around the sun at like 100,000 miles an hour. Something ridiculous. It is breakneck speed. It's going really, really fast. Don't quote me on 100,000 miles an hour, but it's fast, whatever it is. The Earth is going around the sun maybe 30,000 miles an hour. Now, why are we going so much slower than Mercury?
Because we're outer.
We're outer, right? Do we need to go that much faster? The answer is no. The gravitational pull on the sun
Strong.
is much stronger because it's closer to the sun. So the gravitational pull from the sun to Mercury is insane. It's trying to suck it into the sun. So in order to keep it out of the sun, what Mercury needs to do, it needs to go much faster in order to maintain its orbit. If it slows down, what's going to happen?
It's gonna go towards the sun.
If we speed up, what's going to happen?
It'll go away.
We're gonna spiral off into space somewhere, right? So you gotta have them both. You gotta have centrifugal force, you gotta have centripetal force, both working at the same time. One to lock you into orbit, right? One to lock you into orbit as far as gravitational pull goes, but the other locking you into orbit so you don't spin out into space. So you gotta have them both working at the same time. Now, where else do we see this? Well, we follow the planets all the way out. We got Mercury, we got Venus, we got Earth, right?
Yep.
And then Mars, and so on and so forth. And what you notice, the further out the planets get, is,
The slower they go?
that's number one, the slower they go. If they didn't go slower, again, we would lose them. They'd spin off somewhere. But the other thing is that the gravitational pull
Gets weaker.
gets weaker and weaker, so that by the time we get all the way out to the end of the solar system, what's the last planet?
Pluto.
Is it?
Pluto's still there.
It's still there, but is it still a planet?
Don't forget about Pluto.
It'll change, this 2020, there's no telling what's gonna happen to
I
Pluto.
grew
But
up
Pluto,
with
yeah, I grew up with Pluto, and then they took his planet status away, and said, you're not a planet, and then they gave it back, and they took it away again. I don't know what he is. But he's recognized as the furthest planet away, but is it really?
No, because there's whole other solar systems, right?
Well,
Is that what you're asking?
Well, for our solar
Are
system.
you saying in retrospect to our solar system, is it the furthest?
Is it the furthest in our solar system?
There's stuff we can't even
Oh,
determine.
wow.
Technically.
Well, yeah, there's-
no.
What's the next planet in?
The closest Neptune,
Is it-
like after Pluto?
Yeah, the next one closer to us. Is it Neptune? Is it?
Sure.
It
Is
is
it Neptune?
Neptune, yes.
Okay. Who it is doesn't really matter. How it behaves does. Okay, so again, this is not to scale, but the last two planets, the orbits are so elliptical, they're elongated, they're not, all of them are really elliptical, but the last two are so elliptical that sometimes Neptune is further out than Pluto. Okay? So why don't we see that with other planets?
Because their pull is greater.
Their pull is greater, their speed is faster, and it makes it more of a round or a spherical orbit. But these guys, the gravitational pull is so weak on them, they're still in orbit, but they're valence electrons. They're so weakly bound to the sun that sometimes we've got Pluto closer to us than whoever the other one is.
So like the last two of them are like in that egg-shaped sort
They're
of
very much
rotation?
egg-shaped. It's not as bad as a comet, right?
Yeah,
But it's much more elongated than any other planet,
okay.
okay? So what's the significance of that? And how do we apply that to what we're doing? What are the two different ways that we create X-rays?
Electromagnetic.
Characteristic and brims,
Yep.
right? So what's the significance of the nucleus on a brim's X-ray creation?
It pulls it in, swings it
Pulls
out.
it in, right. So what we've got is an electron. Electron in this model looks an awful lot like
Planet.
planets, right? So you take an electron, you get it close enough to the sun, or a planet, and get it close enough to the sun, what's gonna happen? Big problem for the electron. right? Or a big problem for the planet. For the electron, it's gonna change direction, and what does it lose?
Loses a photon.
Speed, velocity, it loses velocity. So what is that velocity? What kind of energy is that velocity? Energy of motion, which is
Kinetic.
kinetic energy. It loses kinetic energy. So it comes in really, really fast, leaves really, really slow if it gets close to the nucleus of the atom, and it kicks off a
Photon.
X-ray photon, right? So what if it passes way out here where Pluto and Neptune would be, or a comet? How much kinetic energy is it going to lose? Not much, right? So what's the energy of that X-ray? Is it going to create an X-ray photon based on how much energy it loses? Yes. But what's the energy of that X-ray photon going to be? Is it going to be real high, like this one? No, it's going to be very low, right? So now apply that to what we talked about in radiation safety just a little while ago. What did Rollins invent?
Rollins invented the collimation.
Collimation and
filtration.
filtration. So these high energy photons, is that what Rollins was after?
No.
No, he's after these Neptune, thank you. Those type loss of energy, right? So very low energy brims X-rays. Now, for characteristic X-rays, what do we have to have? We get an electron,
And it knocks another one.
it's got to knock it out, right? So what do you know about the orbit of Mercury and its relationship to the distance to the sun?
It's
That's really, really
It's going really, really fast, and it's tightly bound or not so tightly bound?
Tightly.
Very tightly bound. So what's the energy of this electron got to be in order to knock that thing out?
It's gotta
Even
be
stronger.
enough.
Very high. Compared to knocking Pluto out, you can push Pluto out of the way, right? But to knock this guy out, it's going to take a lot of energy, right? So what does that tell you about the binding energy of the inner shell electron versus the outer shell electron?
Inner shell
tighter.
is stronger than outer shell.
Very, very strong binding in the inner shell as opposed to the outer shell. So in order to create characteristic X-ray, knock out this inner shell, now this is a tungsten atom instead of a solar system. To knock this thing out, what we have to have is an X-ray beam with 69.5 kVp worth of energy, at least. And I say that because this is bound into place with 69.5 keV worth of energy. Okay? So what if I send this to it with 69.1 kVp worth of energy?
It would be able to knock it out.
Doink,
Yep.
right? Did you create X-ray?
No.
No. Now, back to Mercury. What if our sun got bigger? What would happen to Mercury? What if the sun got more mass?
It would get closer.
It would get closer, and what would happen to portal Mercury?
And die.
It gets sucked in, right? Right?
Yes.
So, we can say that the orbit of Mercury is characteristic to the size of our sun, right? In order for Mercury to stay in its orbit, if the sun got bigger, what would have to happen to the centripetal and centrifugal force?
I feel like it'd have to go fast.
It would have to go faster, right? In order to keep it from falling into the sun. So that orbit, the strength of its centripetal and centrifugal force is specific to our sun size. If our sun got bigger or smaller, then we'd all be in trouble, right? So back to our tungsten atom, that binding energy here is representative of the tungsten atom. What if we added a proton to our tungsten atom? It was at 74, what if we went to 75?
We'd have to add an electron.
You'd have to add an electron to keep it neutral, but what else? Did the size of our nucleus grow?
Mm-hmm.
So what's going to happen to this binding energy?
It's gonna be stronger.
It's going to be stronger. It's got to be stronger. It's probably going to be, the electron's probably going to be going around faster and faster because the centripetal and centrifugal force have to increase, right? And this binding energy is now going to be characteristic of that atom and no longer the tungsten atom.
So it'd be larger.
It'd be greater, so it may be 70.5.
Okay.
Again, that's just a number I'm throwing out there. So, why do we call that the ejection? We're going back to tungsten now. Why do we call the ejection of that electron? Crank this up to 69.5. Eject that electron, now this becomes an X-ray photon. Why do we call that a characteristic interaction?
Because it's changing the characteristic of the tungsten atom.
It's not changing the characteristic of the tungsten atom, it's because that binding energy
Is comparable?
is characteristic of the tungsten atom. If we change the atom, we change the binding energy, we change the energy of the characteristic photon. Characteristic photons that we're gonna recognize, we're gonna see them all over the scale. You know, if we ejected this one, we're gonna create an X-ray photon, it's just gonna be so low energy, we don't care about it. But it's still characteristic of the tungsten atom, because that binding energy is characteristic of the tungsten atom, right? But we don't care about it. So we're not gonna recognize it. The only one that we're gonna recognize is the inner shell binding energy, which is always gonna be at 69.5 kVp, is the energy of the photon that we're gonna recognize in characteristic interaction. Okay? So, why do we need to know the atomic structure? That's why we need to know the atomic structure. Is all that gonna be on this next test?
Yes.
Yep.
We have
Playlists and
that.
everything.
Maybe not all of that, it's gonna be on the next test, but that's why you need to know it, is because to understand how the X-rays are created and how to carry this all the way through 2 years from now when you're taking the registry, you gotta get this, okay? It's not that I'm mean, I am, but it's not that I'm mean, it's that I want you to know this so that when you sit down at the registry, you have confidence enough to not, go on a bender the night that you take the test. Which you might anyway, but that's okay. It's not gonna be because of this, it's gonna be because it's over, right? Any questions?
So the largest it can ever be is 69.5.
That's the largest in the tungsten atom. Again, and so the short answer to your question is yes, because the only atom we're ever gonna use for target in diagnostic X-ray is tungsten. In mammo, they use a different element, it's called molybdenum, and the characteristic photons off of molybdenum are like 32 or 33 or 34, something like that.
You
But it's
said the
characteristic
tungsten
of
the
molybdenum.
tungsten target, the one that's on the anode is what you're talking about? So that's
Yeah.
what the, oh,
Yeah,
sweet, okay.
that's off the target. So this is actually an X-ray creation, this is after the electrons travel across the tube, they slam into the target and create that.
Can I ask a question that has nothing
Sure.
to do with this? So I think I read that like the stator is copper. Is it the stator that's copper or the rotor?
The stator.
Why is it copper? Like what? How is that?
Well,
why?
copper is a good conductor. And
Okay.
we'll get there later in the semester, but copper is a good conductor. Like the wires in
Houses and stuff.
your house, most likely, is copper.
Okay.
For a while, they started using aluminum, started burning down houses. They got away from aluminum, and they use copper for the most part.
Okay,
because
so
it's a good
pretty much
conductor.
just because it's good, okay. I was just
Yeah.
curious because I memorized that and I was like, why do I need to know this?
Yeah, yeah.
Okay, cool.
Yeah, and again, some of what we'll talk about every single time we meet is just planting seeds for later in the semester. I think we have 6 tests. By the time we get to the probably the 5th test, we'll have talked about everything we're gonna talk about this semester more than once. So that, the last test really should kind of be reviewed. Okay?